Good afternoon, everyone. My name is Professor Irene Pennesis. I'm the Research Director in the Blue Economy CRC, and I'd just like to welcome you now to our sixth webinar series for 2022. It's Trends, Challenges and Future Perspectives for Floating Offshore Wind Development. I'd like to just start by firstly, on behalf of the Blue Economy CRC, acknowledging the traditional owners of the land in which we meet today. I'd also like to pay my respects to elders past and present and the Aboriginal and Torres Strait Islander people. For those who don't know about the Blue Economy CRC, we were established with a 10-year life under the Australian Government CRC program in July 2019. We have 43 partners from Australia around the globe, and our purpose of the Blue Economy CRC is to perform world-class collaborative industry-focused research and training that underpins the growth of the blue economy through increased sustainable aquaculture and renewable energy production. Today's webinar is about floating offshore wind developments. Most of you will know or may not know that the Australian government earlier this year released the regulations and proposed cost recovery arrangements under the Offshore Electricity Infrastructure Framework to support basically developments in offshore renewables and infrastructure. And even more recently, in just a couple of months ago, the Australian federal government also declared Australia's first 6 offshore wind energy zones. And I'm really pleased to say that some of that work was underpinned by the Blue Economy CRC's work to evaluate the feasibility and potential of offshore wind and identify barriers to its large-scale development to contribute to Australia's large energy needs. So in our webinar today, and if we can just progress to the next slide, we have a few speakers. And I'd like to say that this will be the first and not the first, but of many other series of webinars that we do on the topic of floating offshore wind. Our industry partner in the Blue Economy CRC is presenting here today, David Carrascosa. He's from Saytech Offshore. And they're going to share a lot of their valuable industry experience and projects in the development of floating offshore wind internationally. We're also going to hear from 2 other presenters that are from the University of Adelaide and the Norwegian University of Science and Technology. And they're going to share some of their research knowledge and experience working on this topic. In fact, the University of Adelaide have been leading a joint research centre with Australia and China looking at offshore wind and wave energy harnessing. And they've been really investigating some of the synergies between offshore wind and wave energy, their interactions towards cost reduction for both of those technologies, and how really to facilitate harvesting of offshore renewable energy in Australia. And I think that's really relevant given that the new infrastructure bill relates to all offshore renewable energy infrastructure, both wind, wave, tidal, and other infrastructure as well. So what I'm going to do now is I'm going to introduce one of our other presenters or co-facilitators from the University of Adelaide. I'd like to introduce Dr. Boyin Ding, and Dr. Boyin Ding will actually take us through and introduce us to each of our speakers today. We will have a Q&A at some cases after some of our speakers and also at the end. I'd really like to encourage you, if I can, to post some questions in the Q&A for us, and we will make sure that we look at them and answer them as the webinar is going, but also address some of them live today in the webinar. Thank you so much for joining. Boyin, welcome. Thank you so much for organising this webinar. I welcome you to presenting this under the CRC, and I'll pass it over to you.
Thanks for opening the webinar, Irene. Thank you very much. Hello, everyone. My name is Boyin Ding. I'm an associate professor at the University of Adelaide, and I am the facilitator of this Blue Economy CRC webinar. I appreciate the Blue Economy CRC provides a great opportunity and a platform for facilitating this webinar, and most importantly, your participation into the webinar. We're pleased to have 3 speakers today to share their insights on the trend, challenges, and the future perspectives for floating wind turbine development. The speakers were invited to provide comprehensive, diverse, but also complementary views on the topic of future floating wind development from perspectives of domain R&D experts who worked on floating wind for many years, domestic researcher who's facilitating the offshore wind deployment in Australia, and the entrepreneur who's leading the global development of floating wind industry. Our first presenter And Aaron Bakinski-Polic is now a professor at the Norwegian University of Science and Technology. And Aaron had 2 years experience as a researcher at ThinkTech Ocean. ThinkTech is also a Blue Economy CRC partner. Aaron will provide an overview of the history of floating wind turbines and their recent development in Europe, as well as the design and the optimization of 10 to 25 megawatts floating wind turbines, draw on Aaron's rich R&D experience on floating wind turbine design over a decade. Our second presenter, Natalia Sergeyenko, is a lecturer at the University of Adelaide and a research topic leader on offshore wind in the Australian-China Joint Research Center of Offshore Wind and Wave Energy Harnessing, which aligns to the Blue Economy CRC's research program on offshore ocean renewable energy systems. Natalia, at this webinar, will provide a review and analysis of scaling laws applied to the design of floating wind turbines. Natalia aims to facilitate a data-driven approach and the rule of thumbs to scale floating wind turbine size up as a general trend in the further cost reduction of the technology. Our third presenter, David Kahas-Kosa, is the Director of Operations at Cytec Offshore Technologies. Cytec Offshore is a Blue Economy CRC partner. David will share an overview on the global floating wind market perspective, discuss key challenges for the industry to overcome, and highlight efforts made by Cytec Offshore to enable a promising future for floating wind industry. Let's welcome our first presenter, Aaron, to kick off the presentations.
Thank you. Let me just try to share the screen. Yes, it's really an honor to be able to be here and say a little bit from my perspective on a brief history of the developments and moving towards optimization as a part of this webinar on the trends, challenges, and future perspectives for floating offshore wind development. If we're going to talk about the history, of course, it makes sense to start with why would we want to have floating offshore wind? And clearly, if we look at wind power density in a global scale, we see that the offshore resources are immense. If we then try to compare this with bathymetry, we can get an idea that moving offshore might be a good idea. And here I've tried to take a map and sort of change the scale so that you can only really see water where the depth is less than 60 meters, which might be roughly where we see bottom fixed becoming not economically feasible. And you can see that there's a pretty limited area which is available. If we then allow water depths up to 400 meters to become available in color here, we see that we've opened up a much greater part of the offshore resource. And that was, of course, the inspiration for many of the projects that have already been started. If we go back to what we'll call the first multi-megawatt demonstration projects, the known projects are Hywind Demo and Windfloat 1. So Hywind Demo was a deep drafted spar, which was installed off the coast of Norway in 2009, while this Windfloat 1 was a semi-submersible installed off the coast of Portugal in 2011. So both are multi-megawatt, but pretty small by today's standards. Then just on a map, we could see them here. If we then speed up a few years and look at operational wind farms today or wind demonstration projects, we can see that a number of new stars have popped up, but actually a number of those are the same concepts still being applied. And that what's happened is that those concepts have just been upscaled in many ways. On the left here, I'm showing how Hywind has grown, and this is very approximate. It's based on publicly available data. Not everything is publicly available, but you can see the 2.3 megawatt demonstration project and what's being installed, partially installed at the moment at Hywind Tampen of 8 megawatts. Windfloat, I don't have an exact model of the Kincardine or other platforms, but they have sort of indicated the size change with this Windfloat Pacific proposal, where you can see how a 2 megawatt prototype compares to a 6 megawatt platform. That's one of the ways that wind turbines, floating offshore wind has been growing. Of course, we also see that more and more projects are being developed. These are a few of the announced ones. If you look at a worldwide scale, you can also see farther out in the future a number of more plans. And I think we'll get more perspective on this global market in the third presentation today. So I'm not going to spend too much more time on that. Instead, I'd like to just give a brief background to the different types of technology that we see being applied, and then talk a little bit about where we go from here, especially with respect to optimization. The technology that we see being applied in this very fancy hand-drawn diagram, we could divide them into the categories of spar. Typically a deep drafted platform with a very small waterplane area has the advantages of being relatively straightforward to install. That's because it's got a catenary mooring system, slack mooring lines, which are relatively commonly used. The manufacturing is simple in terms of the components because you simply have cylindrical components to put together. The disadvantage, of course, is that it requires a large water depth. And when I say it requires a large water depth, that's not only at the location where it's going to be installed, it typically also requires a large water depth at the location where it's going to be put together. So you will maybe use a fjord where you can upright the spar platform so that you can install the tower and turbine on top. And then from that fjord, of course, you need large water depth all the way out to the location where the spar will be installed. And that's not going to be an advantage for every country, but you might see some of the reasons why Norway would have started with a spar. Semi-submersibles are probably the most popular at the moment. These are characterized by these spread columns, which give them stability in a different way. The disadvantage of a semi-submersible is usually that because you have these spread columns, you're going to be more susceptible to wave excitation and might have larger wave-induced motions than, for example, the spar. Advantages, of course, are that you have a much smaller draft and you're more flexible with respect to water depth, and you can maintain this simple installation of the mooring system and just towing out the platform. We also have tension leg platforms as a possible concept, and here you might notice a relatively long list. There is perhaps some bias here since I wrote my PhD thesis on tension leg platforms. These have not been very popular for industry, however. One of the main reasons is that these vertical tendons, which need to be pre-tensioned, are expensive and challenging to install. The advantages could be that we have small motions, and we still have flexibility with respect to water depth, potentially a smaller steel weight, and also potentially an advantage of a small footprint area on the seabed, since we don't have a spread mooring system. That could be a potential advantage in cases when you might want to have fisheries or aquaculture sharing some space with the wind farm. On the other hand, you still have to deal with the power cable in some way, so there remain challenges there. Finally, we could have some concepts that we call barges, which have an even shallower draft than the semi-submersibles that we've talked about. And they have a clear advantage in terms of easy construction, very flexible with respect to water depth. Maybe they can even compete against bottom fixed in some cases. Disadvantage, again, you have a large amount of structure in the waterplane area, and that can have the disadvantage of making you more susceptible to wave-induced motions. I've also put these into this stability triangle, which we sometimes use to illustrate how different platforms obtain their stability. Because of course, one of the first criteria for successful floating offshore wind turbine is that it should float upright. This triangle has a point for ballast stabilized, meaning that you have a large heavy weight at the bottom, mooring stabilized, meaning that you're using the mooring system for stability, and waterplane stabilized, where you're using the waterplane area moment of inertia. And we can kind of categorize those four types of concepts by where they are on this triangle. So we put the spar at the top, the TLP at this corner, the barge in the buoyancy stabilized, semi-submersible somewhere in between. And even concepts that don't look quite like the ones that I've shown so far can be placed on this triangle in some way. If you've heard about the recent demonstrator installed in Norway, from Seasol, it can be placed as a spar because of its heavy ballast at the bottom. And if we look at the SciTech floater, which we'll probably hear about a bit more later, we can see that it would be closer to a barge type of platform. So what is the actual challenge in all of this? And right now, the offshore wind industry is working to try to minimize what we call LCOE, the levelized cost of energy, while maintaining safety. I promised not too many equations in this presentation, but I do have two. And here comes the first one. What is LCOE? It's the sum of the costs over the lifetime divided by the sum of the electrical energy produced over the lifetime. And this is a good way of trying to compare different concepts in terms of the cost for getting a kilowatt to the consumer. If we're going to sum up the costs, those are obviously going to include both the initial cost, the investment expenditures, as well as operation and maintenance over the lifetime. Of course, we have to account for a discount rate here, and the electrical generation, similar, we sum up the electrical generation over the lifetime, and we have to account for a discount rate there as well. Where are we with floating wind? It's a little bit hard to say because there aren't that many projects to look at. But we do have this reference from the DNV GL Energy Transition Outlook, where we can see the comparison of floating and bottom fixed LCOE. 2020 is here on the left. At this point, we can see that there's a big difference. We're not quite at a factor of 2, but still quite a big difference. The projections, though, is that there's going to be a steep decrease in these costs, in this levelized cost of energy. How do we get there? Well, there are two main contributions: upscaling, so larger and larger turbines, and optimization, so improving the technology, improving all the operations and maintenance and the supply chain all the way along. Dr. Sergenko is going to talk about upscaling. I'm going to focus on the optimization part. And before I get into the optimization part, I just want to make one more comment regarding this LCOE, which is that LCOE is a nice measure, but it really doesn't tell us everything. The real challenge that we should be working on should go beyond the LCOE. Offshore wind is a non-dispatchable source of energy. It's intermittent, that's the nature of the wind, and that's hard to compare against a continuous electricity generation. LCOE also ignores environmental externalities, ignores other economic factors, and it's hard to compare new and existing generation. One of the examples of how LCOE might be a misleading unit to apply to compare is if you consider the fact that more and more wind farms are being installed, and the price that you get for the electricity will depend on the other wind farms as well, because it's a question of supply and demand. And now we're seeing that maybe it makes a big economic difference to be able to produce as much as possible in cases with low wind speed when your neighboring wind farm can't produce as much. So there are factors that are hidden when we talk about LCOE. Whether we talk about LCOE or beyond LCOE though, what we saw before was a case of, so we wanted to minimize some kind of cost within some type of constraints. And that is exactly an optimization problem. So an optimization problem, and here, these are my last equations as promised, is defined by saying that we want to minimize something, an objective function. And that we can choose. We can choose it to be the cost of energy. We could choose it to be the negative of profit. We obviously want to maximize profit for a company. We could choose just motions or some other characteristic of our floating wind turbine. We want to minimize that objective with respect to some kind of variables that we can change. So we're going to call those a vector of design variables X. And those are things that we can control: diameters, thickness, shape, controller of the wind turbine. Subject to, meaning we have some kind of constraints, which are either equalities that we have to match. For example, hydrostatic equilibrium has to be satisfied, or some inequalities, structural stresses that we cannot exceed, allowable accelerations in the platform, whatever you might choose to formulate your design problem. In trying to do optimization of floating wind turbines, I would say that there are maybe three main challenges that we have to try to overcome to be able to really use, let's say, computer-based design optimization beyond just human optimization efforts. The first is defining the objective and constraints. Second is parametrizing the design space. And the third is evaluating the candidate designs efficiently. And clearly there's still a lot to be done on this, because if we look at the literature, we look at the market, there are a huge number of designs. And I'm not saying that we're necessarily going to converge to one, but probably we need to work more on defining what we mean by best in order to be able to say which ones will be most appropriate in which situations. So if we look at our first challenge, defining the objectives and constraints, let's think about that a little bit. An objective function tells us what we mean by best. What does the word best mean to us? It's not quite that simple. It has to be something that you can define mathematically, and it also has to be something that you can estimate from the inputs that you're given. And for a computer can only solve the problem exactly as it's posed, and we have to think really carefully about what we choose here. At the moment in research, LCOE is actually probably too complex to calculate completely. Things like installation costs, operational costs, and even the details of construction costs are often beyond our simple tools at the moment. So we're often looking for proxies for cost, maybe mass of steel as a good example, and also for performance, so that we know something about the amount of power produced, but also about the quality of that power, how variable it is, and over time, for example. We also have to define our constraints. So what do we require of this design? Again, same, it has to be something we can define mathematically and something we can estimate from the given inputs. So some examples we might have would be, well, we have to have equilibrium, we have to have a certain amount of static stiffness, so we can't have too large of a static pitch angle. We want it to fit into a shipyard where it could be built. It needs to be able to be floated out. Fatigue and ultimate loads, we can't have it failing too early. And things like nacelle acceleration related to the wind turbine performance might also be considered. If we can define the objective and constraints, we also have to define the design variables. So the second challenge will be trying to parameterize the design space. And here there are a number of choices that you can make. Just to give you an idea of where we are in the research community, this is a first example, which is a 10 megawatt spar. And in this case, the platform and the tower were considered as the design parameters, primarily for the optimization, a little bit of the mooring system and control system as well. The tower and the platform were divided into sections, and each of those sections could be given a diameter, a length, and a wall thickness. On top of that, we also had the scantling design, meaning that we're really trying to look at how much steel you might need in terms of stiffeners and the details there. In terms of the mooring system, there was the fairlead position, mooring line length, the diameter of the mooring line, and the horizontal distance to the anchors, quite simple. And we also included in this optimization the control system. The wind turbine has a controller for the blade pitch and generated torque. In this case, it was the blade pitch controller, which was included in the optimization. And that actually makes a difference. Due to time, I'm not going to go too much into the details of that aspect, though. For a semi-submersible, we could look at parameterizing in a little bit different way. This example is from another PhD student who's trying to generate some candidate 25 megawatt semi-submersible designs. And he started out looking at platforms with a central tower and those with a peripheral tower, meaning that the platform is on one of the side columns. Here you can see sort of the variables that you might need to be able to stretch and shape this type of design to get new designs. What you can see here, of course, though, is that if we start with this shape, we're not going to end up with something radically different. And that's also somewhere where defining your design variables comes in. If you want to end up with something radically different, you're going to have to allow the computer to make radical changes. And we're not really there yet. Finally, the other challenge is to just be able to evaluate our candidate designs efficiently. A floating wind turbine is an extremely complex system. If we look at this image, which I've always thought has been a nice illustration, we can see all the different types of loads. We often talk about aero, hydro, servo, elastic analysis, meaning that we need to take into account aerodynamics, control, hydrodynamics, and structural dynamics at the same time. That's because this is a complex, tightly coupled system. And often we use nonlinear time domain analysis to do this type of analysis. But for optimization, that's often going to just take too long. So we're stuck trying to use simplified models at the moment. And again, I'm going a little bit fast because of time, but we look at just sort of graphically how much we're simplifying this image into my structural model consisting of 3 modes plus the rotor rotation, or replacing the whole platform and its hydrostatic stiffness and the mooring stiffness with springs, masses, inertias, and a few beam elements for the tower. So we're at that level at the moment. Still, we can get some interesting insights by using this. So I want to go through a couple of results very quickly here as well. So the first result that I want to show, this is from the optimization of a 10 megawatt spar. What you're seeing on the right is an illustration of the shape of the platform and the tower. When you look at this, I want you to not be too misled by the fact that we've tried to make things visible. How have we done that? Well, look at the scale. It's actually much, much longer relative to then its width. And if you look at the thickness here, that's exaggerated by a factor of 40 compared to the diameter. So it looks really quite thick, but it's not in reality. Just if we drew it to scale, you wouldn't be able to see much of anything. Here we've ended up with an interesting shape. Does that shape make sense? Yes, it does. We are able to put a lot of ballast down here. We move our center of buoyancy up here, and then we're able to deal with the fatigue loads in the tower by having this sort of thicker section around here. What we can also see by the colors, which on the left are showing the fatigue utilization and on the right, the buckling utilization, tells us the hull is driven by buckling, while the tower is largely driven by fatigue. And one thing you might notice though, is that that tower isn't one that you can buy. Right, the normal towers are linearly tapered. They start biggest at the bottom, smallest at the top. Ours doesn't do that. Okay, fine, we can do the optimization that way too. We can see what happens if we force the tower to be linearly tapered. We can also see what happens if we force the tower to be linearly tapered with a fixed base diameter. And what we see is that if you make those choices, you get a different platform and you get a different cost for your tower and your platform. And those are both larger than what you would have if you optimize the whole system at once. I hope that that's a direction that the industry will be able to go soon, to actually be able to do integrated optimization. One final result that I wanted to show as it relates to the upscaling presentation you'll hear soon is this investigation into upscaling at this and optimizing at the same time. So here we've simply done a design space exploration, trying out many, many different designs and comparing them to a theoretically upscale design. And there's results here for a central tower and a peripheral tower on the left and right. And we'll just focus on these top graphs. What we see is the steel mass as a function of the static pitch angle that you allow for your design. This red line is what we'd call the Pareto front. Those are the best combinations we can come up with. And the green squares are the theoretically upscale designs. And what you can see is that the theoretically upscale designs are really too stiff. They have such a small static pitch angle, and you could get a huge reduction in steel mass if you just accept slightly larger static pitch angle than what theoretical upscaling gives you. And that means that we have room to do optimization at the same time as upscaling. So just to finish off, where do we go from here? Well, in the webinar, we go from here to hearing about upscaling and also from the industry perspective. And from the optimization side, we need to add more industry perspective as well. We need to have more measurements of the cost of installation and the actual costs of construction. We also need to add improvements to our numerical models so we can take additional factors into effect and make sure that they're still in good agreement with higher fidelity models. I think that I've used up my time, so I'm sorry, Boyan, if you're watching the clock carefully, and I'll stop here and thank you very much for your attention.
That's a great presentation, Irene, and also good control of time. Thanks for that. We have a good dozen good questions. So everybody, we're gonna have a final Q&A session for the panel to respond those questions. But for now, given Irene's availability, I will pick up probably 2 to 3 questions for her. I will pick up the first question regarding, can a spar type technology only put upright once towed at the site to avoid the water depth issue at assembly and site? And also associated question associated with that is, what is the maximum water depth for spar type platform?
So for a spar type platform, in theory, you could upright it anywhere, but typically where you want to install offshore wind turbines, you have a lot of wind. And where you have a lot of wind, you tend to have a lot of waves. And that means that you might have too much motion to be able to mate the 2 components safely. So this has so far only been done in protected waters, to my knowledge. Maybe if we can get motion compensated installation systems, that's a direction where one could go, but at the moment it's not feasible. And in terms of maximum depth, that's really a cost issue because the spar doesn't have to get deeper, even though the water gets deeper. It's the mooring system that has to get that longer and typically heavier. So I don't think that there's a maximum depth. I think that so far they've been installed up to around 300 meters, but there's nothing stopping you from going deeper other than the cost of the mooring at the moment.
Yeah, thanks, Aaron, for the insights. You talk about acceleration and motion. So there's a question actually talking about, when you mention different concepts, you speak about the motion of each type. Aren't acceleration actually more important from the turbine perspective than the motions?
So accelerations are often given, acceleration of the nacelle is often given as a criterion for the turbine itself. But we can also consider that there's a maximum pitch angle, for example, that the turbine might accept. So it is a combination of the two. And I was using motions broadly to encompass accelerations as well, but that's a good point.
Yeah. And also another very general question people ask is about environmental impact. They ask about these different platforms, do they have different environmental impact to the, to understanding, Aaron?
Yeah, and it's nice that someone brought that up because that's sort of something that we'd love to include in optimization is really what is the environmental impact. But in order to answer that question, we would have to know, for example, where's the steel produced? Where is it then transported? What about if I use concrete? Where's the concrete produced? What are the emissions during the concrete production? What about the seabed interaction with the mooring system? And how do I weigh those against the carbon production? So that would be a really interesting question to be able to answer, but it's very hard to have enough information to answer it in detail. And it's probably not answerable on a specific concept level at the moment.
Yeah. Thanks, Aaron. Thanks again for the great presentation from Aaron. And we need to keep going to the next two presenters. However, Aaron will get to your questions in the Q&A function in the next half an hour. So our next presenter is Natalia. Natalia was discussing scaling law applied to the design of a floating wind turbine.
Thank you, Boyin. This work has been done in collaboration with my colleagues from the University of Adelaide, as well as with Erin Baczynski College. And I would like to start with acknowledging major achievements of offshore renewable energy in Australia. As Irene at the beginning said, from 2021, we have Commonwealth Waterways of Australia can be used for installation of offshore renewable energy. And from June 2022, we already have a framework for industry to construct, operate, and decommission their projects. And just less than a month ago, the government declared 6 different offshore energy zones, and you can see them on the map. What is important to understand that those zones are not only for wind, for offshore wind, they are common to support offshore renewable, different offshore renewables, including wind, solar, wave energy, tidal, and hydrogen. According to the most recent data, in Australia, there are in total 28 projects proposed and wind farms with total capacity of 50 gigawatts. The technology and wind turbine size varies between the developers. So it's like 7 or up to 18 megawatts. In terms of floating projects, we have around a third of the projects proposed for floating wind. And because the floating wind is targeting deep water conditions, they are mostly located in New South Wales, partially in Victoria, and some sites in Western Australia. So by number of projects for the states, in terms of the states, Victoria now is a winning state with 11 wind farms proposed, followed by New South Wales and Victoria. Oh, and Western Australia, sorry. So talking about my presentation, let's assume that you are a developer and you designed an amazing platform for 5 megawatt wind turbine. It can be 2 megawatt, whatever. You created a platform and you would like to change its size its design, upscale it somehow to support a larger wind turbine. So what should you do in this case? Unfortunately, I don't have an answer to that question, but I did my investigation keeping that question in mind, and I might provide some guidance for industry to follow. So in general, platform developers, they adopt commercially available wind turbines without any changes, and they are trying to manufacture or to design the platforms considering different technical and economical criteria. And I will start, so in order to design a platform, we need to understand what's going on and how the wind turbine is changing with changing power. And then I will move on to the platform. Starting with the wind turbine. Over many years, people were asking themselves how large a wind turbine can be built. And for any engineering system, if we want to increase its size, some parameters, forces change according to the area. Quadratic to the length scale, while other parameters changing proportionally to its volume as a cubic. So if to take an example of the aircraft, here we have, if we want to increase the size of the aircraft, if its lifting capacity will increase proportionally to the square of the length, while its weight will increase proportionally cubically. And it was a discussion. We might have a limit for aircrafts, like technological limit, that they cannot build larger than some particular size. And actually, if to put the size of the aircrafts on of the exponential scale, you can see that, yeah, it was an exponential growth in aircraft size until it reached the plateau. And we don't see aircrafts larger than, let's say, Ria anymore. So is this case the same for wind turbines? And if to take the rotor diameter is a length scale, so power production of the wind turbine will increase somehow proportionally to quadratically to the rotor diameter as a square of the rotor diameter. Oh, sorry, square of the rotor diameter. While cost is proportional to the mass, and mass theoretically will increase as a cubic. And we don't want power production to increase slower than the cost. However, if to put a similar map for the wind turbines, we can see also it was an exponential growth in wind turbine size until they reached like 5-7 megawatts. And now we don't see that huge dramatic increase anymore. So what is happening? So for example, just on this slide, you can see how technology and advances in technology change how the mass of the wind turbine changes with the rotor diameter. And initially, manufacturers were relying on all the technologies, for example, like less polyester. And once they started increasing the length of the blades, the mass was increasing cubically, and that's not exactly what they wanted. And once manufacturing technologies advanced, we can see that we were able to achieve, and the companies were able to achieve achieve now quadratic dependence of the rotor diameter. So blades become now lighter and much cost effective. But blade mass is not the only cost driver. So what about nacelle mass? And nacelle has the generator in it, has a hub and rotor itself. But mass of the nacelle increases cubically. So that's why about 10 years ago, it was several research papers where people questioning, can we build wind turbines larger than 5 or 7 megawatts and for them to produce cheap electricity. But now we know that yes, wind turbines can reach, last year it was a 14 megawatt wind turbine, this year just 1 week ago, 15 megawatt wind turbine was announced. So yes, wind turbines progress and become larger. So, but because the wind turbine design is highly affecting the platform design, we wanted to understand current trends, because the trends I showed you on the previous slides, they were just 5 or 10 years ago. So we took data from 9 different wind turbines, starting from 1.5 megawatt until 20 megawatt. And those wind turbines were designed for offshore applications. Some of them are floating, some of them for fixed. Some of them are not manufactured yet and just on the paper, designed on the paper. And we collected lots of data for those wind turbines, and we tried to understand how different parameters of the wind turbines, power, mass, tower design, change with the increasing rotor diameter. And is there any differences between wind turbines installed on a monopile, fixed, or on a floating foundation? And so the first out of many parameters we analyzed, I will show you just several. We found, for example, power is changing as diameter to the power of 1.8. It's a bit less than square dependence as theoretically predicted. But what about mass? We put like Bill's analyzed blade mass, nacelle mass, tower mass, and I was glad to see that, yeah, now with technology advances, we can able to, the companies and manufacturers were able to achieve that close to quadratic scaling law for all the mass components. What's also interesting that wind turbines starting from 10 megawatt, like 10, 12, 15 megawatt, they start utilizing direct drives instead of gearbox. And it was lots of discussion whether the generators for direct drive wind turbines will become heavier. But we can see that, for example, here, gray dots on the plot showing the wind turbines with direct drive. And they are quite perfectly aligned with the general trend. So we can see that direct drive does not really change the mass change, the change in the mass of the nacelle mass in total. So what about height? Unlike onshore wind turbines that are installed higher and higher in order to capture stronger winds, offshore wind turbines, regardless of whether it's 1.5 or 20 megawatt, they are like designed in such a, should be installed in such a way that there is a clearance between the water surface and the lowest point of the blade tip. And that clearance around like 30 meters in order to leave the space for ships to go. So in general, again, we analyzed lots of different criteria, but in general, we found that with current trends, power increasing as like close to quadratic dependence on the rotor diameter, all linear dimensions, tower height, diameter of the tower, thickness of the tower, also change linearly with the rotor diameter, mass, quadratic dependence. What's also interesting that all those wind turbines, whether it's 1.5 or 20 megawatt, they are targeting, like they designed for rated wind speed close to 11, 12 meters per second. So we cannot say that large wind turbines, they target stronger winds. They're designed for similar wind conditions, I would say. So when we start moving to floating platforms, what's the difference? And we have now, in addition to lots of disturbances, of course, wind is changing in time, and across the rotor we have rotating blades. We have new sources of disturbance like waves, ocean current, and tide. So that is why we need to, companies need to reconsider, maybe they need to change the control system of the wind turbine. Maybe they need to change the tower in order to accommodate those disturbances in the design. So what's the main differences? I mean, there are lots of differences between wind turbines designed for floating or fixed applications, but I'll just put here as one of the main differences that I noticed. So we have a tower, and in order for that tower, I mean, we don't want the tower to be vibrating with rotating blades. So we have a rotor frequency, which is called 1p usually. We have blades passing the tower, which is called 3p frequency. And we don't want those situations to excite the tower, and so it starts vibrating. That is why people are carefully choosing and designing towers in such a way that the natural frequencies of the tower, avoiding those shaded areas. And so the natural frequency should be somewhere placed in between 1p, 3p, and so on. So, but if to put a similar map on like along different wind turbines, let's say you have a horizontal axis, which is rotor diameter, and frequency as a vertical axis, and we see the shaded areas, we would rather to avoid for design of the tower. So, and if to put on top of this map natural frequencies of towers designed for fixed applications, for fixed foundations, and we can see, yes, manufacturers are trying to put natural frequency somewhere in between, so the tower is not excited by rotating blades. But once we start putting the same tower on a floating foundation, we have waves, and that's not what we want. Because you see the trend is with rotor diameter going larger and larger, the tower will start being excited by the waves. So if to put on top of this map again, tower designs specifically for floating applications, we can see that developers are trying to put them a bit higher, so avoid that wave excitation region at all. So the general rule is towers for floating wind stiffer, heavier. Diameter probably is kept the same as for fixed and floating applications, but walls should be kept thicker. Now moving on to the floating platform. How to design the floating platform? Lots of industry partners here, everyone knows. So the platform should just float, should support, it should not sink, it should support the tower, mass of the tower and turbine. Also, the main idea of the platform that it should keep the upright position of the wind turbine, and the maximum allowed angle of the motion is less than 10 degrees, like from the vertical. Also, specifically for the semi-submersibles, that draft should be kept more than 50 meters, while freeboard should be more than 10 meters. And of course, the platform should be stable enough, and its motion in waves should be minimized. So now going to the key question. Let's say you have a platform designed for 5 megawatt. What should you do in order to redesign it or change its size to accommodate 20 megawatt wind turbine? We reviewed lots of different approaches proposed in literature by the industry, and we identified 3 different scaling laws. So the first scaling law is called, we call power scaling. So the main idea is you need to increase the size, linear dimensions of the platform in a similar way as linear dimensions of the turbine. So if the turbine increased twice, diameter of the turbine twice, then the linear dimensions of the platform should increase twice as well. However, with this approach, mass and cost of the platform increase faster. So it leads to much heavier and much more costly platform, which is over-designed, but much more stable. The next scaling law is called mass scaling. So we don't talk about length anymore, we talk about mass. So if the mass of the wind turbine increase 4 times, okay, we need to increase the mass of the platform also 4 times. But in this case, platform dimensions will increase slower. But this trend is really close to the existing trends observed in industry. And the last scaling law is called fixed draft. So the same, we are talking about masses. Mass of the wind turbine should increase, mass of the platform should increase in similar way as the mass of the turbine. But with the constraint that we need to keep the draft of the platform the same. So either it's 5 megawatt or 20 megawatt, the draft should be 20 meters, say. So in this case, the horizontal and vertical linear dimensions of the platform scale differently. And we did a numerical analysis of, we compared all those 3 different scaling laws, and we identified that the last scaling law leads to much larger nacelle accelerations, which is really undesirable for the like for the platform developers and Turbine. So, but what's exactly going on in practice? What kind of designs proposed and what is common for those designs? We identified 8 different like semi-subs. We focused just on semi-subs, and we took 8 different designs. And of course, we couldn't get any common features. So some of them using 3 columns, some of them using 4 columns, some of them using braces, some of them like heaving plates and so on. So it's hard to get what's common for those designs. But the main question we had that maybe there is a parameter that is common for all of them. Maybe there is some features once the developer is trying to increase the size, maybe there is a parameter that is related to the rotor diameter. So, and again, we collected lots of data, and you can see the differences in design, some using passive ballast, some active ballast, some are made from steel, some are made from concrete, some like draft completely different, starting from 13 meters, like up to 30 meters. And the contribution of the platform to the total mass of the system varies between 80% and 90%, or 96 even. But still we try to identify what is a common design parameter which drives the design of all those platforms. So in terms of the semi-sub, what is that length scale? So we had a look at several parameters, but 2 major parameters is a distance to the main, to the offset column, which is called R here, and also the diameter of the offset column, I put T here. So we tried to identify the trend. Of course, not enough data, 8 points is not enough, might be, but still we couldn't get good fit, so poor fit. So distance to the offset column is not scaling proportionally to the rotor diameter. Then we checked, maybe that's a diameter of the offset column which is changed proportionally. And again, we were getting poor fit. Maybe that's a mass, and again, poor fit. So until like we played with lots of parameters and we identified that's a product of the distance to the column and the diameter of the column. So, and because that parameter drives the stability, pitch stability of the platform, that's a common thing that all the companies trying to keep it the same for regardless the size and regardless their design. And also what's interesting, talking about natural frequencies, across all the designs, across all the different wind turbine sizes, all the developers trying to keep natural frequency of the platform in heave close to 20 seconds. And you see that, yes, those platforms can be excited by waves and will move with waves, but heaving motion, like up and down motion, is not really critical for the power production, while pitching motion is very critical. That's why developers are trying to keep the natural period of the platform in pitch quite higher outside that wave excitation region and close to 30 seconds. So in general, just to what we have found that platform linear dimensions have not increased proportionally to the rotor diameter. Developers try to keep the platform draft close to 20 meters. Natural periods for the platforms across different sizes and designs kept similar. Contribution of the platform to the total mass of the system tends to decrease, but slightly. And some platform developers try to use mass, active ballast to decrease the mass. And just the last bit, take-home messages. So if you want to design a platform for larger wind turbines, and the wind turbines parameters, you cannot find wind turbine parameters, they are not released by the manufacturers. You can use our data to extrapolate the data to mass and inertia properties for larger wind turbines. Then in terms of control, you can consider modifying the blade pitch control to ease the requirements for the platform design. Then tower, consider designing stiffening tower for installation on floating platforms. And also, if you want to upscale, I would start from mass scaling law. So you can start from that, increase the size, increase dimensions, see how it performs technically and economically, And then you can follow the optimization, like explained by what was explained by Erin. And initially we asked ourselves how large a wind turbine can be built. We don't know the answer to that question, but maybe the platform design will be the limiting factor. And that's a question that can be answered by industry-university collaboration. So thank you for watching.
Thanks, Natalia, for the great insights. I think that must be very useful for the industry to go ahead. What I will do is directly invite the last presenter of this webinar, David, to provide insights from different perspectives, industry perspective, the market perspective, and also from the operation perspective. So David, go ahead, please. And then we will have the Q&A session at the end to trying to answer all the questions.
Thank you very much. And thank you also for having me today. It's an honor to be able to share some insights from the projects we've been doing so far. Okay. Good. So let's start by explain a bit what's SciTech. So SciTech is a global company, still in the medium size, but with a global ambition, I would say. We are an engineering company with more than 300 employees, 30 years of experience, mostly in the civil engineering field, but then also growing in terms of being a more of a multidisciplinary company. We've been always very committed to R&D and innovation, and proof of that is let's say the development we've been doing in floating offshore wind. So for the last 10 years, we've been developing a patent of a floating offshore wind platform from, let's say, sketches, numerical models to a full-scale demonstrator unit that I'll present afterwards. To, let's say, have a kind of a separated business unit, we launched our spin-off, SciTech Offshore Technologies, which I'm leading at the moment as an operations director. And through this spin-off, we are focusing on, let's say, the commercialization of this floating offshore wind technology with more than 35 colleagues and projects in different levels of development, different levels of commercialization, but also worldwide. Having said that, I'm here today to provide a bit of a flavor of what's the market, which are the challenges, and also what is SciTech doing in floating offshore wind. So starting in let's say the market view, Erin did an introduction about the technologies. I will look more at the opportunities and the size of the upcoming market. So for now, we have, and speaking only about floating offshore wind, we have 120 megawatts which are operational. Those are distributed along Europe and Japan mainly. Also China has some units. That figure will now increase in 88 megawatts with the Turbine project when this one gets operational, but it's not still operational, so we are still in that 120. Aside those 120, there's 170 megawatts which are secured. So final investment decision has been taken, and then these are projects that will happen. But what's much more interesting is what's in the right-hand side of the table, or say the slide, which is the amount of gigawatts. It's not megawatts now, it's gigawatts that it's in development. We have now, and that's a slide from from a renowned consultancy, the Renewable Consultancy Consulting Group. They have, let's say, they have been mapping the floating offshore wind market, and they've recognized almost 113 gigawatts in development, which is massive, and it's also showing the potential for floating offshore wind and how this is being captured by the companies, by the developers. But obviously, developers, utilities won't be developing this much of floating wind if there's no roadmaps. So the good point is that we have several roadmaps, programs, auctions taking place, and that's what this slide is all about. So we see some kind of center of gravity now in Europe. But the truth is that both Asia Pacific and North America, and now starting in South America as well, and as we know for the latest announcements also in Australia, the news are booming with new roadmaps, say new auctions. We will start in France with the first commercial auction this year. That's a 270 megawatt auction that is aiming to get the very first floating offshore wind commercial farm into operation before 2030. And yeah, I won't stop into each of them because we've got limited time, but I think it's sufficiently interesting for the let's say the global companies to then push for developments. So if we go to a summary again from the Renewables Consulting Group, we've got to understand that even if we will have auctions happening this year and for the following years, those auctions and let's say the megawatts that will be tendered, the amount of megawatts will increase significantly over the years. It takes time. It takes time from, let's say, the award of a wind farm, 200, 600 megawatt wind farm, to the execution of that wind farm. Let's think that once a project is awarded with a tariff and with a connection to the grid, then you will start the environmental impact assessment, which will last about 2 years. Then you will be doing in parallel some engineering, but then the procurement process, the permitting. So all those steps need to be taken, and in say new and emerging markets, times tend to last a bit longer. So we can be awarded project now in 2022, but probably the commissioning date won't be until 2027, 2028. So a minimum of 5 to 6 years is the time that we will see between let's say the auction and the installation. Why I'm explaining all that, it's also related to this specific graph. I said there will be auctions this year in 2022, but we don't see the installed capacity reflected in the graph until 2028. Good point is that we expect by 2030 6.4 gigawatts to be installed, but then in 1 year, in 2031, just in 2031, we expect 9.3 gigawatts to be installed. So 1.5 the overall capacity installed in the floating wind history just in 1 year. So we can see how this is being exploding, and this is evolving exponentially. But obviously, let's say, as any emerging industry, that comes with some challenges. And well, my colleagues today have already explained a bit about what's the sizes of the turbines and some of these challenges. But if we look back to what was the first onshore wind farm back in 1982, those turbines had a height of about 12 meters over height. Then the first offshore wind farm in Denmark, using 450 kilowatt turbines. Those turbines had a 34 meter tower, and then if we go to the right, we reach the 12 and then the 20 megawatt wind turbines with dimensions which are impressive. You've got an example with the A380, which is 80 meter wide, and it's impressive how it compares. But I think we actually need another slide to see what does say a 12 megawatt wind turbine looks like. So those turbines have a 220 meter rotor. That means 107 meters in terms of blade length. You can see in the upper right part of the slide the comparison between that Airbus A380 versus the blade. This is a slide from General Electric, which is very visual, because you can see the comparison with the Turbine or some other buildings that we all know about, and we all understand the sizes of it. So that's how impressive things get in offshore. And on top of that, we've got to put that on top of a floating platform. What do we do in SciTech to understand the sizes? Well, as I said, we've been developing a platform technology that we'll get into the details of it afterwards. But if we take one of these 12 megawatts and we put that on top of our floater, that's how it would look like if we compare to our local stadium, the Athletic de Bilbao. But a football pitch is something that we all have in mind, right? So that's the comparison between the turbine platform versus a stadium, which I think it's very visual. Let's go now to some other things that are also a bit challenging, and that's a table coming from RWE, our partners in the 2 megawatt project, the demonstration project, and a wish list of what a port the kind of characteristics and features required in a port to accommodate the construction of a commercial size floating offshore wind farm. We see the quayside water depth be ideally greater than 12 meters, having not an impact on tidal. The dimensions we need are in the order of 50 acres, so more than 20 hectares. We need also, if we are going to transport the floaters already assembled through a channel, that channel needs at least 200 meters in width. We will have structures that will have an incredible height, and then that needs to be taken into account if we are going below a bridge or power cables. Then we've got to have also sufficient wet storage area. So that means area in the port to storage the floaters, because you will be producing floaters along the whole year, but you will be installing floaters offshore only during the installation season. And that installation season will depend on the weather you will find in your location. It's not the same installing platforms in the North Sea or in the Mediterranean Sea, where the Mediterranean Sea will have a much larger installation season because of being, the wave regime and so on. It's much lower compared to the North and North Sea, for example. So yeah, this is kind of some things will have to be met, or requirements from ports. And I can tell you, after analyzing ports worldwide, that these kind of things are very difficult to be met by a single port. So just in summary, what's under our point of view, some of the key challenges for commercial development of floating offshore wind. So first, it's that availability of area in ports. It's easy to say that we need an area which is greater than 20 hectares. Ports are not usually there waiting for floating wind to reserve 20, 30, or 40 hectares area for 2025 when you will be executing your projects. Now, ports are there to take profit from every square centimeter of their area to generate cash flow for the project. So that's a kind of a key point. Then also regulatory frameworks are key. It's usually kind of bottleneck for the development. So the industry is ready, but then the regulatory framework and the structure for the auctions and so on is not ready for the projects, and that's something we need to push for. Then again, every market is an emerging market for floating wind, and supply chain is usually not prepared or not really ready for the sizes of these units, the amount of chain that has to be produced, the amount of steel, concrete. So we need also to support the supply chain for them for us actually to be ready for these next steps. And then in terms of social response, it's very important to educate people, to educate the different stakeholders, to present projects to the different stakeholders from the very beginning. So to environmentalists, but also to fishermen, also to say the workers' unions. That depends a bit on the geography for sure, but everywhere in the world where you will like to install floating offshore wind will most likely be the first time floating offshore wind will be installed, and then you've got to explain what does it mean. Then just a view on what SciTech is doing in floating wind very fast, because I'm running out of time. We've developed a technology which is I would say yes, a barge type technology. Actually, it's a twin hull concrete platform using a single point of mooring as mean for the attachment to the sea. We see a great potential for this technology to be a very competitive one, and also great, let's say, enabler for local content, and that's something we've proven through the DemoSat project, which is the first full-scale project we developed. That's a project that's using a 2 megawatt wind turbine. It's a project in collaboration with RWE, the second bigger company in terms of offshore wind assets worldwide. And yeah, it's a great company. It's our first project in terms of being a full-scale project, but it's also the first floating offshore wind turbine that will be connected to grid in Spain. So it's also a great milestone for the country. We're installing the project in Leiden, which is a test center with the cables already laid. That's a test center which is located in the North Atlantic coast of Spain, and it's a very harsh environment. We will have maximum waves of up to 20 meters. That's for the 50-year return period. So that's the value we use for design. And yeah, it's a very harsh, but also it's a very good place for a proof of concept. Yeah, I won't stop too much here because I mean it's been a very kind of pushing project because SciTech has played the EPCI role for the whole project. So we spent quite a few hours in engineering. We've engaged more than 30 companies, and also the project team has had to be significant, like more than 100 colleagues. And regarding local content, that's I think a very important slide for us, because we managed to award 75% of the construction budget to companies that are based 25 kilometers around the port of Bilbao, which is massive in terms of how these projects can support local content. And I would just like to show you what does actually launching operation, a float-off operation of these units look like. So you can also realize a bit the sizes, even if this is a 2 megawatt platform, it's already big and it's very interesting. We've been hearing all their studies about Pirineos. And the good point is that that one is also scaling very well. If we go from 2 megawatt, 15 megawatt, dimensions have a filling factor of 1.5. So the house diameter that are 12 meters or 12 meters to 18 meters, the mass will have a factor and again, concrete is very interesting material for the development of because of how competitive it is factoring and also the presentation, I would just say that, well, we are not stopping at the demonstrator. We are obviously working now on commercial auctions, but we are also developing our own projects. There's 2 projects that are being developed in in Spain, one in the north, one in the east. These are 2 times 50 megawatt projects. And we are also involved in a pre-commercial project in California, which is intended to be the very first floating offshore wind project of the coast of the, let's say, of the West Coast in the US. And to conclude, just a few things. So it's obviously required to have research to analyze what's the trends, what's the collaboration between university and industries is very much required to keep on innovating, to keep on optimizing. But I think an important message is that floating offshore wind and the technology is ready for commercial deployment. It is also the most suitable technology for emerging markets. You don't need a huge fleet of installation vessels for floating offshore wind. You can manufacture your floaters in the existing ports. Obviously, the ports will need some optimization, some adaptation, but then we will be able to get into deep with no need of jackups or big vessels. It's a huge opportunity for local supply chains, and finally, we need obviously for these and let's say not kind of having this problem of bottleneck. We need the support from regulators and policymakers. That's a must. And that's all from my side. Sorry if I've taken a bit longer, but I think that there was a few important messages.
Thanks, David, for the very exciting and promising, presenting such a promising future for floating offshore wind from the industry perspective. So now everybody, we're coming to the panel discussion. So what I will do is flag some of the commonly asked questions to our presenters. So David, I think a lot of questions are around the environmental impacts. Could you please share your insights from an industry perspective regarding how you make sure there's minimal environmental impact from your technology?
Yeah, so I would say that in overall, floating offshore wind compared to fixed bottom offshore wind has usually a lower environmental impact. So that to say, compared to what's being the trend in terms of offshore wind, we are locating floating bodies, and then the connection with the seabed is through anchors and chains and catenary moorings. So the impact in terms of the mammals, the peace in life, and let's say the noise and so on, it's highly reduced. But having said that, to get to a point where you're able to install and operate a floating offshore wind farm, you will always need to go through at least 1 year of surveys, of offshore surveys, to analyze every single potential impact. And it's been quite hard to get to the point where you are allowed to install. So I would say that I wouldn't be too worried about let's say impacts, because we are super highly controlled by the administrations, and that's happening in every single country and every single geography we are developing projects.
Thanks, David, for that. Natalia, I saw there's a technical question for you regarding your statement, the minimum draft to be greater than 15 meter. Could you please clarify that statement?
Yeah, I put those guidelines from the book, and it's mostly because of the semi-subs, they're quite wide. And if we have the big body and if it starts like tilting, it has a pitch, you might experience such a situation when the lowest point of one side goes above the water surface. And when it goes back, it can experience slamming, so which is really bad for like in terms of fatigue loads. So that's why in order to prevent that situation, it was recommended as a starting point to use 15 meters for semi-subs.
Thanks, Natalia. David, seems like lots of the audience is very interested in your technology. They feel it's very interesting. So the question they have is, how did you actually come up with such a design? You know, what's the motivation behind, and how that compare to traditional platform in terms of advantage? Yeah.
I would say this is coming from an out-of-the-box thinking, I would say. As said at the beginning of the presentation, SciTech group is coming from a civil engineering mindset. So that's why concrete was actually the material to select. And then the geometry itself it's kind of a catamaran ship-shaped platform. And that's coming because we understood there were several topics that had to be brought to floating wind for a technology to be feasible and interesting. One is the reduced draft. We have a draft of about 8 meters for the 2 megawatt device, and it will be below 11 meters for the full commercial units. We also need platforms that navigate very well, and that's the case for our platform. We may have situations and projects where the port where you are manufacturing your platform is 150 kilometers from the final area or the site of the project, and then being able to tow the unit faster compared to others will make it very competitive in terms of matching the installation seasons. As I said, those installation seasons can be fairly reduced depending on where you are, and then let's say the fact of having a curved geometry is the way the concrete behaves better, and that's because of our understanding in terms of the concrete structural behavior. And finally, it's not the technology, but its construction process is also thought and developed to industrialize the technology. So that's also where we're coming from.
Yeah, thanks, David. I think I will just raise one last question. Is also, I think for David is the best person to respond. What is being done to review blade design and function to reduce collision risk to birds? Now that's a very real question, right?
No, that's an interesting point, and actually it's interesting because we have gone through a very long permitting process for our 2 megawatt demonstrator off the coast of Spain, and it's been a long permitting process because the area where the platform will be located is actually an area which is protected for birds, and we are using actually a device which is called DT Bird. That DT Bird device is a scanner for birds, and in case of imminent collision, this device would actually have the capacity to stop the turbine. So the project will not only be a prototype for the technology, but also a great, let's say, base for the study and analysis of the impact for birds. So I think I don't have the, let's say, the answer now on what will be the precise impact, because we are entering into operations now in October this year. But what I can assure is that we are taking the measures to avoid any kind of impact into the birds.
Yep. Thanks, David. I think it's about time for this webinar, so we'll handle it to Irene to thank everybody.
Thank you, Boyne, for doing a wonderful job introducing the speakers and handling the Q&A. You were an excellent co-facilitator. I want to take the opportunity just to thank Erin, Natalia and David for your really interesting and valuable presentations. I want to thank all the people who joined the webinar today. Just to let you know that we will be making the recording available on the Blue Economy CRC's website, and you'll be able to listen to this webinar again in the future. The CRC's been working in the space, of course, with floating wind. It's a very important part of our program in looking at sustainable offshore renewable energy developments. And we will be looking forward to introducing more webinars on this topic. So if you've got an interest in presenting as part of any of our future series of webinars, please reach out to us on the inquiries and we'll be back in touch. Thank you very much, everyone, and goodbye.